or is it okay? There was a comment like that. Okay.
It's fine.
It's fine. Okay. All right. Okay. So let's then go back to L functions. So what we were doing was, so last time we saw first the convergence issues. So if you define, okay. So for any, so things like this, summation 1 by n to the s or summation an by n to the s, they converge for absolutely for s bigger than 1. And they converge uniformly on if you take something away from 1. Okay, so that is okay. And so one example of that is the zeta function itself, Riemann zeta function, which converges for s bigger than 1. This doesn't converge for s equal to 1. In fact, near s equal to 1, this is the behavior. That is what we saw. It blows up like 1 over s minus 1 plus something that stays bounded. This zeta tilde itself, it actually converges on 0 infinity. So zeta s minus 1 over s minus 1 actually converges on, is well defined on 0 to infinity. Also, zeta itself is not defined at 1. And then we went to the case for L functions. In L functions, we have these ANs, which are complex numbers, but they are oscillatory and there is a lot of cancellation. So we saw this other thing that if partial sums of ANs are bounded, then this series an over n to the s summation converges for s positive and uniformly on anything like delta infinity. Now that we showed, and as a consequence, L functions, Dirichlet L functions for non-trivial characters converge for non-trivial characters, they converge for s in 0 to infinity. And and because of uniform convergence on delta infinity, they define continuous functions and all that. Similarly, okay, for the trivial character, we saw it is actually almost the same as zeta function. It's not, it's zeta function times this product. If we put 1 everywhere, it is zeta function, but here we put 1 where it is coprime to D. Therefore, we get this other product. So, but it's more or less like the zeta function. Its convergence is on blah, blah, blah. So at s equal to 1, it will have this behavior. Okay, so now we came to the product formula. So that is where I was. But are there any questions before I start resuming here? Okay, so we wanted to put product formulas for these things. So first thing is that if A is a multiplicative function, completely multiplicative function, and we assume A is bounded, then this summation an over n to the s has this product formula valid for all s bigger than 1. Okay, so both sides converge. This is a partial sums converge to this. Here partial products converge to this and they are equal. Okay, so they are continuous functions of s. Left side we already know. So it's the question of why you get the right side. So what we did is, so we first restrict to a finite product. Okay, so this is valid for s bigger than 1. So if you order the prime numbers, okay, so if you order the prime numbers as p1, p2, etc., and let's take the product of 1 to k, meaning p1 to pk, this right side, but only over the first k prime numbers. Okay, so when this is written, of course, when an infinite product is written, it means it's a limit. Okay, so that is to be understood. So this product 1 minus ap over p to the s is this 1 plus ap over p to the s plus ap square over p to the 2s and blah blah blah, which is summation an over n to the s for all prime for this. Now everything is absolutely convergent here. Okay, so there's no problem. You can just write this product. So this what you get is you get the product. So when you expand it, you get the product over a p1 to the e1, ap to the e2, apk to the ek, and divided by p1 to the e1, pk to the ek whole to the power s. So over all e1 ek greater than equal to 0. This means we get things like this is an by the multiplicative nature of a. Therefore, we get an divided by n to the power s. Okay, n is so we are calling p1 to the e1, pk to the ek as n. Then we get an over n to the s, and all those n's will come exactly once. All those n's which have prime factors among p1 to pk come exactly once, and everything else does not appear. Okay, nothing else appears. So this includes 1. Okay, by the way, so if you want, also n equal to 1 is included here. So because that is also part of the product. So this part is okay. There's no problem with this. Everything is absolutely convergent. You can rearrange, do whatever you want. Okay, so AS are bounded, these things are absolutely convergent, no problem. So now just let n go to infinity. K go to infinity. Okay, so what about this? So if you take this, so let's give this a name. So okay, so this is okay. Forget it. So the what I want to say is that summation an by n to the s n in n prime factors are among P1 up to Pk. If I take that and I subtract, let's just subtract n equals 1 up to Pk, an by n to the s. This is bounded by whatever is the supremum bound on A times summation 1 by n to the power s, n bigger than Pk. Right? So what happens here is that, so here this is an infinite sum, but it's not a big deal. Everything is absolutely convergent, so I will not worry too much. But basically what cancels are, what remains are those numbers which do not have prime factors in P1 to Pk, or at least one prime factor outside of this. So certainly all numbers up to Pk have prime factors in P1 to Pk. We have ordered them. So what remains is at most all numbers bigger than Pk. Okay, it's a big overkill, but it doesn't matter. Anyway, this goes to 0. And so therefore, this quantity converges as k goes to infinity to, it converges to summation an by n to the power s. N equals 1 through infinity, because the definition of this is a limit of these things. As k goes to infinity, Pk goes to infinity. Therefore, this will converge to an by n to the s. So which shows that hence the product must also converge. Hence the product converges. That is, the definition of the infinite product is the limit of this as k goes to infinity, and equals to that, and equals we get product 1 over 1 minus AP over P to the power S. This product over primes, by definition, this is limit k going to infinity of product j equals 1 up to k, 1 over 1 minus APJ over PJ to the power S, which is actually, anyway, this is, as we showed, an by n to the s, n equals 1 through infinity. Okay, so this is true. For those who have seen other things, so you can use other stuff to, if you want, short circuit some parts. So it is something that anybody who has taken a course in course in complex analysis will have seen. So you may recall that if you have functions from okay, so from some domain, okay, from some domain to complex numbers, such that summation mod Fn is finite. So this converges, let's say, uniformly on omega. Then product 1 minus Fn also converges uniformly on omega. Okay, strictly speaking, I should. Yeah, okay. Roughly, this is correct. So this is. So this you can do it that way also, if because summation AP by P to the S that converges uniformly on S bigger than 1 plus delta, right? Because A's are bounded and this is P to the power S. So this convergence of this was a priori clear if you knew this lemma. Anyway, so this proof is showing that it actually converges. Okay, so one point is that, so what about, so in particular, so as a corollary, we get so if chi is a character, if chi is a character of ZD star, then its cell function is equal to product over all primes 1 over 1 minus chi of P over P to the power S. So this is true for S bigger than 1. Okay. So this is a, because just directly from there, because chi is a, since chi is a, so it follows from here as chi is multiplicative. Chi is bounded and so you can take chi of n in place of an here. Okay. Oh, sorry, did I start recording or not? No, okay, I have started. Okay, so that's why you get this product formula for the L function as product 1 over 1 minus chi P over P to the S. But note that we have put it only for S bigger than 1. So this is not, I mean, although for, although this is for non-trivial chi, this converges for, this is well defined for S positive, okay? But product formula is for S bigger than 1. So that is still the case. The product formula is for okay. So this is the product formula which we wanted to establish. Any questions, comments on this so far? Okay. So then let us. What is it that we need to do? So the thing that. So now I already gave a sketch, but maybe I'll have to recall that again of how this. After all this, we will proceed. Okay. So maybe I can try to find it. Right. So this was the basic point. Okay, so what we want is to study the sum of the reciprocals of prime powers to the power S in our arithmetic progression. Our arithmetic progression is A plus D, A plus 2D, and so on. Okay, so that's our arithmetic progression. And what we want to show is that there are infinitely many prime numbers there. The way we will do it is we take this sum with S bigger than 1 and show that it blows up as S approaches 1. Okay, when S decreases to 1, this blows up. That can only happen if there are infinitely many primes. If there are finitely many, this will be a finite number. So that is what we need to show. So we consider this sum of reciprocals of prime powers in the arithmetic progression, primes in the arithmetic progression, which can be written with an indicator function. Because we want P only in the AP, we can write P congruent to A mod D 1 over P to the S. Now, there we use the Fourier analysis of ZD star to write. So we are assuming also A comma D is coprime. So A without loss of generality, we may take A to be in 0 to D minus 1. But of course, it's not 0. It is coprime to D. So this is A is coprime to D. So A indicator A is a element of ZD star. So which we can write the Fourier expansion of indicator A. That's what we did. Indicator A, the Fourier expansion. But then we have extended the functions to all integers and blah, blah, blah. So we write it in terms of sum of characters of ZD star, chi A bar, chi P over P to the S. This is the indicator A inner product chi will be this. And then there is a 1 over phi of D, which is the size of the group. This comes because there is a 1 over the square root of that in the definition of Fourier coefficient and all that. Okay, so just in the definition, there is a 1 by square root n, etc., wherein is the size of the group. So we get this chi A bar, chi P over P to the S, sum over chi. I mean, this is just, this is the indicator A of P. Okay, so this is the indicator A of P bar, where P bar is the residue of P. So that's why we get this Fourier expansion. And then interchanging the character sum, this is a finite sum, this is an infinite sum, we can interchange. So this is chi A bar and chi P over P to the S, 1 over phi of D is outside. So the point is we got this thing. So what we got was this. Summation 1 by P to the S. Here, this sum we separate into two parts. We write the trivial characters separately and we write the non-trivial characters. For the trivial character, we get 1 over phi of D chi naught of P over P to the S. Okay. And every prime is going to be coprime to D. Okay. So, I mean, okay, at least after the first one. So this is just 1 over P to the S. Essentially. So this is fine. This part is there. And then we have the sum over all the non-trivial characters. So what we want to say is that one is, first of all, this blows up as S goes to 1 and none of these things blow up. So there are finitely many terms. One of them blows up, the others don't blow up. Therefore, the total blows up. Okay, if even two of them blow up, you have to be careful that they don't cancel each other. If two of these summands, if for two characters we got blow up of this quantity, they might cancel each other and the total may not blow up. But it's exactly one summand that will blow up and the rest will not blow up. And that is what we want to show. Okay, so this is, remember, so this is the what I am trying to recall, that we have to show this, that this blows up. For the trivial character, it blows up, and none of the things for the non-trivial character blows up. Okay, so we want to prove that. Once we prove that, we will be in good shape. Okay, so that is the point. Is that okay? So this is what we are trying to prove. So let me just write here. So the goal blows up. This is actually 1 anyway. Chi naught of P, I mean, except the first one, I mean, maybe D is a prime, I don't know, but so there may be one prime in there, but that's all. Okay, so P, chi naught of P is actually equal to 1 except one term. At most one term. So this goes as S goes down to 0 and is bounded.
Oh, Manju, you mean S goes to 1 or?
Oh, S goes to 1. I said that, I wrote S goes to 0. Or maybe I missaid also. S goes to down to 1. And chi of p over p to the s stays bounded as s goes down to 1 for all chi not equal to the trivial character. So once we prove these two, then we will be done. Okay, so that is the part which is that is actually the thing. So how do we do that? So what I was the idea is the heuristic idea, how the heuristic idea or that you to take logarithms here. Okay, so that is the idea. So log, it's like you may recall that this is actually well. So this comes from okay, if you let's do it for the trivial character. Okay, so for the trivial character, what do we know? I mean, they also it is true, but this is all one, right? So so when chi is chi naught, so this is L chi naught of S is product 1 minus 1 over chi naught of p over p to the s, and it's almost same as, so this is actually zeta of s times product 1 minus p to the, what is it, 1 minus p to the minus s, p divides d. All those primes which divide d, it is that product. We saw it last time, right? So L chi naught, we had this right. So we had this thing, so we get that. You also see it actually in this product formula actually. So you also see it here, because the what happens here, you get a you get a reconfirmation of that here. See, what is this? This is over all primes, right? So the primes that are, so when we take this, so this is actually over all p that are co-prime to d, right? Actually, yeah. So I should have no, I made a mistake. Actually, it is one. So it is one, except I said at most one term. No, that's not correct. It's not one, except finitely many. That divide d. Okay, so if it divides d, chi naught of p is 0. If it doesn't divide d, it is 1. So this product, when p divides d, this is 0. So you just get a 1 in this factor. So you might as well take over product over primes that are co-prime to d. So that's what this is. So what we have is basically this. So this is actually the same as the zeta product function. Okay, so the zeta, I mean the product formula for the zeta function, Euler's formula. And then you remember that everything came. So that is, we are back to summation 1 by n to the power s equal to product 1 over 1 minus 1 by p to the s over primes. And then you can take logarithm. Let's just write log zeta s is sum of log 1 minus 1 by p to the s over primes. And that is same as because 1 by p to the s plus 1 by 2p to the 2s, 1 by 3p to the 3s plus dot dot dot. Okay, and these things all converge, so you will just get summation 1 by p to the s plus this entire thing can be written as 1 as s goes down to 0, s goes down to 1. So this whole thing, there is no problem. I mean, even if there are infinitely many terms, I think I have written it in the notes. I'll put it up. But you can take it as an exercise yourself. See, summation 1 by p to the 2s, you can bound by summation 1 by n square over all, because s is bigger than 1, that you can bound by summation 1 by n square. This can be also bounded by summation 1 by n cube and so on. So you can just sum this entire thing together and it will stay bounded as S, even as S goes down to 1, there will be no problem. That will stay bounded. So what stays is this, and this one blows up. This and log zeta of S, zeta S behaves like 1 over S minus 1 plus big O of 1 as S goes down to 1, right? Hence, log zeta of S blows up. As S goes down to 1. Okay, so maybe is it to minus infinity or plus infinity? What did I do? There's a negative here. Oh, yeah, there's a negative. Something is a bit fishy. Hold on. Sorry, there was a minus log of 1 minus. There was a minus. This is all in the reciprocal. This is minus log of 1 minus 1 over p to the s. So all this becomes plus actually. Yeah, I forgot. So this is blowing up to infinity. So hence summation 1 by p to the s goes to infinity, from which we get that summation chi naught of p by p to the s also goes to infinity as s goes down to 1. Okay, so this is the justification for this. Chi naught of p over p to the s blows up to 1. Is that okay? So I think I had done this sort of, but yeah. So anyway, this is one of the things. So what about this side? How do we show that this stays bounded? Okay. The point is that here the corresponding L function.
That first line is the inverse, I guess. Heuristic idea, that first line.
Yeah, this one. Yeah, right. So here itself, I forgot to put the. This is all with the inverse actually.
And 1 over 1, it says 1 over p to the s, right?
This one.
That line again.
This is okay. Sorry, say again. Where
Yeah,
here?
like, 1 over p to the s, that should be 1 over p to the s.
No, this here you mean. Sorry, some places I have written p to the minus s actually. No, this is. I see. Sorry, I wrote. Okay. Yeah, this is. Yeah, what did? Okay. Sorry, I don't know. I have written some gibberish. I put the reciprocal in the wrong place. Sorry about that. I hope that didn't cause any confusion. Probably not. So this is, yeah, thanks. So it was 1 minus chi naught of p over p to the s reciprocal, 1 minus 1 over p to the s reciprocal. And then took log, and basically what we got was to get the summation 1 by p to the s behavior. We are using this product formula to relate it to the zeta function near s equal to 1. What happens to the zeta function at s equal to 1? And the zeta function at s equal to 1 blows up. Therefore, summation chi naught of p over p to the s blows up. Okay, so this is the gist of it. Is it okay? Sorry for that, some gibberish I had written. I hope it's okay. Okay, so now how do we handle the non-trivial case where we are supposed to not show it blows up, but that it doesn't blow? So the basic point is similar. The thing is, we will again use this to relate it to the L function, but now it's not the zeta function. And now we know that the other L functions actually have no problem at s equal to 1, right? So these other functions, their problem is at s equal to 0. So not at s equal to 1. So as s goes to 1, if you follow the same approach, it should show that following the same approach, heuristically following the same approach, So we would write log L chi of S equal to minus log of 1 minus chi of P over P to the S. Right? So that is what we get from here. And then you will write this as summation chi of P over P to the S plus chi of P over 2 times P to the square over 2 to the 2S plus blah, blah, blah. And then this is basically, this is not, I mean, this part, since the reciprocals have a much higher exponent, more than 2, at least 2. So this is big O of 1 as S goes down to 1. There is no problem. That will stay bounded. And what is, and this is the one that what we are interested in. This is what we are interested in. And so the blow up or non-blow up of this should come from this side. But this L chi has no problem at S equal to 1. In the sense, it is finite. That is, L chi is actually is continuous on 0 infinity, because chi is not the trivial character. However, log can still have a problem. So there are okay. So more or less, so that would suggest, okay, so let me just write, suggests that summation chi P over P to the S has no problem as S goes down to 1. There should be no blow up is the suggestion. So, but of course there are two problems here. So can somebody say what is the problem?
Goes to 0. So log
Right.
of 0
So
is not.
there is a problem of this log. We have this side we have the log, and even if L chi of 1 is 0, then there can be a problem. So two issues. One, if L chi of 1 is 0, then L chi of 1 will be minus infinity, and so that's a problem. So in fact, that may cancel this. That is an issue. So that is one thing. So this is actually a key point. In fact, this is the gist of the whole proof. This is where it comes to that the L function does not vanish at 1. That's what we will show. Okay, so that's where that will be the big thing to show. But more basic than that, there is another problem. What is that? Another issue with this. So the question is, what the hell is this logarithm? See, here everything was okay. We had positive numbers, everything is okay. Here we have complex numbers, chi of P over P to the S, and L chi of S is also a complex valued function. So what is this log? Okay, can we take log like this? So that is actually first thing that one should resolve. Okay, so otherwise it doesn't make sense formally. That's why it's a formal proof. If you don't ask questions, then it looks okay. But if you ask what does it mean, then it falls apart. So the log is not meaningful. Okay. Some of you will have seen, of course, when you have taken, if you have taken complex analysis course, you know that logarithm is a tricky issue, and but there are also ways to deal with it. And but I will not assume you have seen it before, so I will just tell you how it is done. So the log business. In fact, even if you know the log business in general, you will need to worry about how it is made sense of here. Okay, so the problem is with complex numbers. So if it is not clear to someone, problem with log in complex numbers. how do you define it? Okay, so what do you define as log of z? Okay, so log z should be w, where w is such that if you exponentiate it, you will get z. Okay, so that is what should be meaning of log z, right? Any number whose exponential, a number whose exponential will give z. But the problem is that in complex numbers, if w is one such, then w plus 2n pi I is also work. For integer n, because e to the 2 pi I n is 1. Okay, so there are many numbers whose exponential is 1. All these imaginary numbers with 2n pi in front of them. So therefore all this work, and there is no way. How do you choose one of them? So you might want to choose the one where the argument is something, but then you will have to give up. So you can't do it continuously. So if you want to pick that w, so you can adjust so that this imaginary part comes. Let's say you will, so w plus 2n pi I means what? You have some w and you have w plus 2 pi I, w plus 4 pi I, etc. And so you have all these numbers which are above each other. And if your real line is somewhere, maybe you will just pick the one in minus I pi of this and I pi of this. So one can do all such things, but the problem is you can't do it in a continuous fashion. Okay, so that's where, so then log will become discontinuous if you try to do that. So you'll have to be careful about log. So this is the issue. So we can't just write log. And also once you do that, it's no longer true that log zw is log z plus log w. Okay, so if you restrict like this, if you fix the argument to be within minus pi to pi, or I mean the imaginary part to be in minus I pi to I pi, then you can restrict, can choose w such that imaginary w is in minus pi to pi to make it unambiguous. But then it is not true that log zw equal to log z plus log w. That kind of thing is not true, which is what I'm doing here. If you see, I had the infinite product and I want to take the log and write a sum of logs. Okay, so it's a serious problem there for me that it is then it is not correct, right? So one has to fix this issue. So if one assumes a bit of complex analysis, one can invoke some things from there, but it's not, this alone can be fixed, not a problem. So yeah, but any questions about this? So modulo that, this is the point. So this is what we want to prove, that this one is done, chi naught of p over p to the s, that sum diverges, we are done. It is this other thing, that summation chi of p over p to the s, that it stays bounded. That is what I need to do, and it will require a little bit of work. Okay, a very big thing that we will do is this non-vanishing of the L function at 1. Okay, so just to tell you, I mean, in fact, this is how in analytic number theory, important number theory aspects will reduce to some zeros of some L functions and such things. So I had announced in the advertisement that the course that I may touch on prime number theorem. I'm unlikely to do that. I don't think there is time. But just to tell you something like this. So in the prime number theorem, what is prime number theorem? How was prime number? Okay, what is prime number theorem? So just so a slight digression. So prime number theorem tells you that phi of x, which is number of primes less than equal to x, that it goes like x over log x. Okay, so that's how, or if you like, some people prefer to write, I mean, so 1 over log t dt. So maybe 2 to x. Now this is a slightly better formula, but anyway, these are the same thing. So prime number theorem is a fundamental theorem in number theory. I mean, it tells you how many prime numbers are there up to x, that it goes like x over log. This was a big thing. I mean, people like Gauss could not prove it. And when it was proved by Hadamard and Delavallee-Poussin, the main point, the proof, the standard proof, at least, there are other proofs now, but the standard proof basically makes it equivalent. In the standard proof, prime number theorem is immediately implied by, it's more or less equivalent to that, that zeta of s is not equal to 0 for all s with real part s equal to 1. Okay, so you consider, so you can extend the zeta function to the complex plane also, right? I mean, so as I mentioned the other day, so at s equal to 1 anyway, it is infinity, so that's not a problem. But nowhere else on that imaginary axis, imaginary line above 1. So this is 1. Nowhere on this line it vanishes. That is the great theorem about. That is actually what implies the prime number theorem. So it's like it's an going further from Dirichlet. Dirichlet didn't go into the complex plane, but the information he wanted was in saying that it does L functions don't vanish at 1, and here it is that the zeta function doesn't vanish on this line, entire line. And the Riemann hypothesis, of course, is that it doesn't vanish even further inside. So there's half here, so that it doesn't vanish. So that it doesn't vanish anywhere here, the zeta function, that is the Riemann hypothesis, which is completely open, or whatever, open, let's say. Although there are, if you search, you will find hundreds of proofs, purported proofs of it. But of course, none of them is right yet. So this is how the analytic information about vanishing of certain functions goes to number theoretic information. And even the Riemann hypothesis, the reason for this conjecture that Riemann had was that it would give him better control of error terms in the prime number theorem. Yeah, this is the leading term. What is the error term? If you could prove the prime number theorem, I mean Riemann hypothesis, it would say that the remainder term is roughly like square root of x or something. I think so. If I'm not mistaken, something like square root of x, I think. So, but anyway, so that's an aside. We will probably not go to prime number theorem. So this vanishing, so so we'll probably not go there anyway. So that is the end of the digression. So let me come back here. So we have to make sense of log, and we have to then show that L does not vanish at 1. And then this proof, then I will come back to this point and fix it. And once we do this, we will be done. Okay, so then that summation 1 by p to the s will diverge for p in the arithmetic progression. Okay, any questions, comments? No? Okay, so now then let me just. Okay, so now let's see. Yeah, what is it we want? Yeah, first, what is log? Yeah, which one should I do first? The L function non-vanishing, maybe I will do later. Okay, what is the plan? Okay, so yeah, what is log? So one place where, I mean, a very simple one, I am following here Stein and Shakachi. They worked out, I mean, minimal exposition which works. So for example, just for log on complex numbers, forget log of an L function. Okay, so we have to take log of this L function. But let's talk about the log of this. Okay, so one place where we can define log is on the disk of radius. Okay, so this is all Z complex numbers such that mod Z minus 1 is less than 1. You can define log Z as by the power series. Okay, so sorry. So this Z is 1 plus Z minus 1. So it is actually defined by Z minus, yeah. It should have a minus 1 to the power k, right? So sorry, Z is 1 plus Z minus 1. And what is log of 1 plus x? It is x minus x squared by 2 plus x cubed by 3 and so on, right? So it's alternating. So here I'll have a, so it will become 1 minus z to the power k. So there is a minus 1 to the power k. So this is 1 minus z to the power k. This is the naivest way to define logarithm. It is defined only on this part of the complex plane. So those who have taken complex analysis, of course, they know much better. So it is defined here. So this is 0, this is 2, and 1 is here at the center. So it's so log is defined on this. So does it make sense? Well, why do you call it log z? Because if you exponentiate, you get so this, first of all, this converges and uniformly on z minus 1 less than 1 minus epsilon for all epsilon positive. So if you take any smaller disk, the convergence is uniform. So that is one, and it is legitimate to call it logarithm because exponential of that okay, so this is 2 e to the, if you raise this to the, that is the exponential has no problem. So you can just yeah, how do you do this? I mean, so you can just I don't know if I want to do it. Yeah. Why would you get that? Yeah, is it even easy to? Yeah, exponential of this sum you can write as product of exponentials, but yeah, for z inside the, so there is no problem for if I take z inside here on the line, it is okay. And but for all z here also it is okay. Yeah, how do I say that? Now, if I use a little bit complex analysis, it's okay. But has everyone? I assume not everyone would have seen complex analysis, so I'm not using any holomorphic functions and business like that. But then maybe I will just leave this as exercise or something to look up in Stein and Shakachi. Okay. So you at least agree when z is on the real line, 0 to 2, this is the usual expansion of the logarithm, right? Yeah, okay. So one way to do that is, actually you look at this as a function of z and see what differential equation it satisfies roughly. Yeah, that's what, yeah, okay. So, right. So if you differentiate it, then you will get it. Okay. I mean, so if you formally differentiate it, differentiate the exponential, what do you get? You will get e to the and then the if you differentiate this, oh okay, actually that doesn't make sense. That will okay, sorry, it makes sense. So k comes down and you get 1 minus z to the k minus 1 and then minus and minus 1. K equals 1 up to infinity. Yeah, something is which is what is this actually? This is e to the summation 1 minus z to the k over k equals 1 up to infinity, and this is a geometric series. So what is this? 1 minus z to the k minus 1. So it is 1 over 1 minus of 1 minus z, right? So we get something is off.
Is there a minus 1 missing from the definition of log z?
Sorry, say it again.
You are using log 1, expansion of log 1 minus x there, right? In the definition of log z.
Yeah.
Shouldn't there be minus x, minus 1 somewhere?
So I got z as 1 plus z minus 1. So I get powers of z minus 1 to the power k, but alternating this. Oh, okay, there was an extra minus here, is it? Yeah, maybe. Okay, I have messed up. So maybe it is a minus or plus. Yeah, but still, what I wanted to say was, okay, I'll not even try. So let me just leave it. So there is a log well defined here, and this will give you the log. Okay, look up Stein and Shekach. Let me just erase this.
Don't we get sigma 1 minus z per k, like as you said, a geometric series?
Yeah, but I was getting what 1 over z, right?
Yeah, I think the minus sign probably fixes it.
Yeah, so there was a sign mistake, which was so I get whatever this left side function is, I get something like phi dash of z is phi z divided by z or something like that, maybe. Right, okay, maybe that is what is I needed actually. Is that the right one? So certainly the derivative of z satisfies this. Z dash is 1 by is z by z. So that is correct. So you have to argue that since they are equal on this, then they satisfy the same differential equation. So they are actually equal. That's what I was heading to. But okay, but I
Sir,
will.
you said formally because we don't know if we can make sense of derivative and all that, right?
No,
Why did you
that
said
can
formal?
Right, that is that no, it's not actually that part is not formal. This justification to do what I was doing is perfectly okay. You can write this exponential as a product of exponentials, but again you need to. I mean, it is again a little bit of justification is needed. I mean, if you haven't ever seen it, I mean, but because there's an infinite series involved and you are differentiating term by term and so on. But these are reasonably easy things, so not a problem. So, but maybe I will skip that. The point that what I want to prove is that this is actually but the problem is that log of zw will not be sum of log z and log w. But what we want to prove is that this is the key lemma, key point. So then log of 1 minus chi p over p to the s is well defined for all primes and for all chi. since chi is has absolute value 1 and p is at least 2, so this has absolute value at most 1 and s anything positive for any so all this is well defined because 1 by p to the s will have absolute value less than 1. So this has absolute value less than 1, so log of this makes sense. Okay, so no problem. According to this, we'll use this as the definition. Okay, and that's what I had here. In fact, it's well defined, and it is what is it well defined as? It is just well defined as that chi of p to the j over p to the j times s. And there is an extra j here. J equals 1 through infinity with a negative sign. So let's put a minus log here. Minus log of this is just going to be this. Okay, so this is well defined. This series converges and all that. But the claim that we have to justify to prove when I take the sum
It's
of
1 o'clock.
Okay, I will finish just after stating the claim. If I take this sum and exponentiate it, then I do get the L function. So I wanted to say log of the L function is this. What I mean is that the exponential of this will give me the L function. So this is what I need to justify, that this e to the this sum of the logs will give me L chi of s for all s bigger than 1 at least. Okay, so this I will do next time. Okay, I hopefully I'll finish off next time, or maybe that product, I mean the non-vanishing of L function may take me to the lecture beyond, but this week I should finish. Okay, so that's all.